To recapitulate what we have learned previously, we have learned how to define sets. We have learned their representation of sets in set builder form or roster form. We have seen the definition of finite, infinite, and empty sets. We have seen the definition of equivalence of sets. We have seen that sets have subsets and power sets. And we have also seen that interval of real numbers written as sets. We have seen that sets can be represented graphically using Venn diagram. In this lecture, we are going to learn union of sets, intersection of sets, difference of sets, and complement of a set. The first thing that we are going to learn is the union of sets. Consider two sets A and B graphically shown here. Now suppose that we want to perform union of these sets. The union of these sets will give another set which will have all the elements of A and B taken together. The union of sets can be graphically represented in like this, and the formal definition of union of sets is a union of sets give another set which has element x such that x is in A or x is in B. Now there are some properties of operation union that needs to be learned. Suppose that we want to find union of two sets A and B. We can either find A union B or we can find B union A. The result will be the same. This is called commutative law. Now again, suppose that we want to find union of three sets A, B and C. We can group any of the two sets together. Result will be the same. This is called associative law. Union of a set A with an empty set will give the set A itself. This is called law of identity. Union of a universal set with a set A gives the universal set. This is called law of universal set. And the union of a set A with itself gives the set A itself. This is called idempotent law. Next operation that we are going to learn is the intersection of sets. Suppose that we want to find the intersection of sets A and B shown in this Venn diagram here. The result of the intersection of these sets will be all the elements in the sets A and B which are common to both. These common elements are shown in the this shaded region in this Venn diagram. Mathematically, it can be written that intersection of sets A and B gives all the elements x such that x is in A, also x is in B. Similar to union of sets, intersection of sets also follows some laws. If we take intersection of two sets, the order in which the intersection is taken is not important. That means intersection of a set A with set B is equal to intersection of B with set A. This is called the commutative law. If we take intersection of three sets, we can group any other of the two sets together and the result will be the same. This is called the associative law. If we take intersection of a set A with an empty set, the result will be an empty set. This is called law of empty set. If we take intersection of a universal set with set A, the result will be set A. This is called law of universal set. If we take intersection of a set A with itself, the result will be the set A itself. This is called the idempotent law. Now if we take intersection of a set A with the union of sets B and C, this is equivalent to taking intersection of set A individually with B and C and then taking the union of the results. That means the intersection distributes over the union. This is called distributive law. The distributive law can be graphically proved as follows. The left hand side of the distributive law is A intersection B union C. Now the in B union C is graphically represented here with this in the all the elements of the B union C are represented in this blue region. Taking intersection of this with set A will give a result, and the resulting elements are in this shaded region. The right hand side of the distributive law is A intersection B union A intersection C. Now A intersection B is represented by this shaded region, and A intersection C is represented by this shaded region. Taking a union of these, we will get all the elements in this shaded region. And as we can see, this shaded region in both this left hand side and the right hand side are the same. Therefore, the left hand side of this equation is equal to the right hand side of this equation. This shows that A intersection B union C is equal to A intersection B union A intersection C. The next operation that we are going to learn today is difference of sets A and B. Suppose that we want to find A minus B, and the A minus B are graphically shown in this figure. The result of A minus B will be all the elements in set A which are not there in B. And the A minus B is shown either by this blue region in this Venn diagram. Mathematically, this can be written as A minus B is equal to all the elements X such that X is in A and X is not in B. The last operation that we are going to learn is the complement of a set. The complement of a set is always taken with respect to the universal set. Suppose that we want to find the complement of a set A. So the set A is graphically shown here, and the universal set is graphically shown here. The complement of set A will give a set having all the elements inside the universal set that are not in the set A. So all the elements outside the set A within the universal set is the complement of set A. Mathematically, complement of set A is written like this. The complement of set A gives all the elements X such that X is in universal set and X is not in the set A. There are some properties followed by complement set. If we take union of set A with its complement, the result will be the universal set, and if we take intersection of set A with its complement, the result will be an empty set. These are called complement laws. If we take complement of union of sets A and B, the result will be intersection of complement of sets A and B. And if we take complement of intersection of sets A and B, the result will be union of complements of sets A and B. These are called De Morgan's law. If we take complement of set A, the result will be the set A itself. This is called law of double complementation. And if we take complement of an empty set, the result will be the universal set. And if we take the complement of universal set, the result will be an empty set. These are called laws of empty set and universal set. There are some other properties of set operations that they follow. The number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus number of elements in A intersection B. If we add the number of elements in set A and B, the element common to both A and B, which are represented by intersection B, is added twice. Therefore, if we subtract number of elements of A intersection B from the sum of number of elements in A and B, we get the result of number of elements in A union B. This law can be further extended to the union of three sets. Suppose that we take the union of three sets A, B and C. The number of elements, if we take the number, add the number of elements in A, B and C, we add the common elements in A, B and C and A and C twice. Therefore, we need to subtract the number of elements of in the intersection of these sets. Therefore, we can subtract the number of elements in intersection B and the number of elements in B intersection C and the number of elements in A intersection C. If we perform this subtraction, we see that the number of elements which are common to all three sets A, B and C are subtracted twice. Therefore, we need to add the number of elements in the intersection of A, B and C, and this will give the number of elements in the union of sets A, B and C. To summarize this lecture, we have seen that the union of two sets A and B is a set of all the elements in A and B. We have seen that the intersection of two sets A and B is a set of all the elements common to A and B. We have seen that the union and intersection of sets are commutative and associative. We have seen that the intersection of sets is also distributive, that is, intersection distributes over union. We have seen that the complement of a set A is a set of all the elements of the universal set which are not the elements of the set A. And we have seen that the complement of sets follow De Morgan's law. That's all for this lecture.